The next step will be meshing. So like I said, if you just follow this workflow from top to bottom, we will be able to complete our simulation. So the next step will be meshing, and we will use, if you right click on meshing, we will use the watertight. Okay, if you click here, mesh, on the right side you have the use workflow is already selected. This box is already ticked, and the workflow type is watertight geometry. So we will use this workflow, watertight geometry workflow. And when we double click on, right click, you can click edit, or we'll double click on mesh, we'll go to fluent meshing. Once you double click, this is you will have fluent launcher, so you can click double precision, and you can select the number of you can determine the number of processes that you can run simultaneously in parallel. So this depends on the number of core that you have, right? Let's say we set this as the more cores that you have, the more core that you can set here. So I'll set this as 4 for meshing and 4 for solver, and click start. This is the ANSYS fluent meshing app. So there are different kinds of meshing apps or software in ANSYS, but this is this fluent meshing is directly under fluent. So you can see here, you have, it looks familiar. You have on this left side, you have this workflow. This is what we call the watertight geometry workflow, and then you have save menus are on top, and you have a console right here which shows all the information of the processes that you're doing, and then you have this window right here. So this is very intuitive. If you just follow this workflow from top to bottom, we will get working mesh. So that's what we will do. We will start by importing our geometry. Since we already have our geometry in the workflow itself in Workbench, so we just click import geometry, and the geometry will be automatically imported into fluent meshing. So the file format is scanned, and you don't have to change anything. Just click import geometry, and then fluent meshing will import geometry into this workflow. So when it is done, you'll see a tick next to it. So we have already imported our geometry, and this is, you can see the geometry here. Okay, so the next step is to add local sizing. Local sizing means that you will add different sizes based on the area or surface of your geometry. In this case, we will add local sizing. Click so change this to yes. We will add local sizing based on the names of that we have, the label that we have set, the name selection that we set. So we will choose this inlet and we will name this as inlet outlet, because we will use the same size, face size for the inlet and outlet. The target mesh size is in this, by default is 0.009, so or 9 millimeters. We need this to be smaller. Okay, let's say we set this as 0.00 0.001. Okay, and we choose inlet and outlet. Alright, so when we do this, this is probably our outlet. We can see this box here. So this box is, the size of this box is 0.001 meters or 1 millimeter. So this box shows you what the mesh size will be. Alright, so if we want this to be smaller, let's make this a tiny bit smaller. Let's change this to 0.008. 0.008, and you can see that the size becomes smaller. So this corresponds, this box shows you a visualization of what the mesh will look like once the mesh is created. So let's stick to this, maybe a little bit smaller, maybe 0.001. Zero point 0.5 millimeters. Okay, so let's use this size. Let's use 0.0005 meters or 5 millimeters. So 0.5 millimeters. So 0.5 millimeters will be the size of our mesh on the inlet and outlet of our fluid. Make sure we only select inlet and outlet here, and once we're done, we click on add local sizing down here, and the local sizing will be added right here. You can edit this by clicking here and clicking revert and edit if you want to edit anything. Okay, once this is done, we can click on generate the surface mesh. So this is the size, the minimum 0.00, the maximum size of the mesh that will be created, and this represents the maximum size. And if you look somewhere here, you'll find a smaller box which will represent the minimum size. Okay, it's somewhere here, we don't need to find it. We now know the size of the minimum size, we know what it looks like. Okay, so for the surface mesh, let's set the minimum size to 0.001 and the maximum size to 0.2. So this is 0.2, the minimum size. When we click here, the minimum size, you should be able to find the red box that represents the minimum size right here, but it's too small to see. And we can right here. So this is the minimum size of the mesh that will be generated, but not on the inlet and outlet, because we have already set the size, the local size of the inlet and outlet faces. So the surface mesh will be on all the other surfaces. So the minimum size will be 0.001 or 1 millimeter, and the maximum size will be 20 millimeters. Right, and once we've changed these values, we can click generate surface mesh or update, and the mesh will be created. So it will take a while to create the mesh, but Fluent will create the mesh automatically for you. And once it is done, the process is done, you can see the information that is related to the mesh down here. For example, you can see the name of the region is fluid, the name of this, we set this as fluid, and then you have you'll have the value that shows skewness, and then you have how many faces that you have in this mesh, and all the other information. Okay, so you can also zoom in and you can see what the mesh looks like. Okay, you can also insert clipping plane here, but we'll do that later. Okay, we will not think too much about all this right now. We just want to have mesh so we can run a simulation. Okay, so this is the inlet or outlet face, and you can see that the mesh size is smaller because we set this local size. We add local sizing, so the face has target mesh size of 0.0005 or 0.5 millimeters. Once we have generated the surface mesh, we will go to describe geometry, and this is where we describe our geometry. So this geometry type, the geometry consists of only fluid regions with no void. This is our case. We do not have any void, and it consists only of fluid regions. Okay, we only have fluid, and there are no voids in our fluid region. So this is what we select, and change all fluid boundary types to wall to internal. No. And do you want to apply shared topology? We don't have any shared topology. No. Enable multi-zone meshing? No. Okay, so we only have to change the geometry type. And once this is done, we can click on describe geometry, and then we also have to update our boundaries. Okay, so we have 3 boundaries: inlet, outlet, and wall. So our boundary inlet will be with the velocity inlet. So we will assign velocity values to the inlet, and the outlet is pressure outlet, and wall we can set this as wall. Of course, you can change it to different kinds of geometry boundary type, but it is for the time being it's not necessary. So we will assign velocity values for our inlet and pressure outlet and also wall. So we click update boundaries, and then the region type is fluid. This is not solid, it's fluid. The region that we have is fluid. We click up, we don't have to change anything. Click update regions. So by the way, ANSYS knows about all this region because we already named it according to the corresponding boundaries. So we set the name of our inlet as inlet, and the name of our outlet as outlet, and the name of the wall surface as wall. So Fluent automatically assigns the appropriate type according to the names that we have prescribed. And then next is add boundary layers. Okay, we have to take into consideration our mesh has to take into consideration the effects of boundary layer. So the boundary layer is a thin viscosity dominant region that forms along a surface of a solid body as fluid flows along it. Okay, so for example, so if we look at a pipe or look at a plate, for example, let's say we have a flat plate. Okay, and you have flow coming in from this side. So this region down here, close to the plate, it will affect due to the viscosity of the fluid itself. You will have what we call the boundary layer, and this boundary layer region is very important. So what will happen is you will have when the flow interacts with this plate, we will have this region where viscosity plays an important role. It's affect the viscosity in this region, the viscosity of the flow. It reacts with the surface of this plate. Okay. Outside of this region, the viscosity does not react with the plate. Okay, but inside this region, the viscosity of the fluid reacts with the plate, and then this is the what we call the boundary layer region. Okay, this is where viscosity is dominant. So we have to consider the effects of viscosity of the flow. So this region is very important because it plays a significant role in defining the overall fluid dynamics of the problem. So it does not only affect it does not only affect the fluid flow in this region, but also it affects the fluid flow outside of the region, the entire region. So we have to take this into consideration. We have to give special attention to the boundary layer while performing simulation, because it will affect everything. Okay, so the accuracy of the simulation is dependent on the ability for us to capture the physics close to the boundary, close to a solid boundary where you have the boundary layer. So we need to be able to create a high resolution mesh that can capture the boundary layer flow physics. So that is what we are going to do, and we will do this by using inflation layer. It means that we will put a mesh where the layers will be close to each other, like this, and it will be so we will have mesh that is very close to each other, layers of structured mesh, so it can capture all these effects here. Okay, so we will do this right here, and so right here we click yes, add boundary layer. We will add boundary layer. You can name this as boundary layer, okay, or anything else. We don't have to name it if you don't want to. It's a good practice to name it if we have a very complex geometry. We have tens of different regions. Maybe we should name it, but for this case it's just one pipe, one fluid region, so we don't have to name it, change the name. Let's set the number of layers to 5. This is just a number. We don't have to think too much about it right now. This is just to show you what it looks like. Okay, let's increase the number to 8, for example, and this is a transition ratio. What will happen is this boundary layer will transition from a tightly spaced region to a bigger spacing. Okay, so we can play with these numbers to get a different growth to the layer itself. Let's just click add boundary layer and see what happens. Okay, we don't see it yet, but once we generate the volume mesh, we'll see what happens. Okay, so we will use polyhedra. We can change the type of mesh, the type of mesh that we like to use. We can use tetrahedral mesh, hexagon mesh, but we are using polyhedral mesh here now. So we don't have to change anything else, and click generate the volume mesh to see the final mesh that we created. once the meshing process is done, okay, so this is what it looks like. So this geometry is clipped in the middle because of here, because this is usually it will be automatically selected, so it will insert a clipping plane, so you can see what the mesh looks like in the middle of the fluid. Okay, we don't need to look at it. If you don't want to look at it, you can just untick this box. So this layer here, this is the boundary layer. This is the layer that we set here. So we'll have 8 layers. 1 2 3 4 5 6 7 8. So we have 8 layers. The distance between the layers is smaller, closer to the wall, and it gets bigger and bigger. This can be adjusted using the transition ratio and also growth rate. And this will be added only grow on only walls, so this will be automatically added only on walls, and we can change this here if you want to. So but this is basically what it looks like. So this is this is what we hope. This is the mesh that we set, and we hope this mesh will capture the effects of boundary layer in this pipe, although we know that this is not good enough, but we will just run one simulation and see what happens. So once we have done this, once we have generated the volume mesh, so this is done. So we already have a mesh that we can use, and we can see the quality of the mesh right here. Okay, the information related to the mesh can be seen here, and you have the number of cells. For example, this is 1.4 million cells, and you have the quality. Since this is a polyhedral mesh, we don't have to think about the skewness and everything, but this will be explained later. Okay, so once this is done, you can save the project. You can also export this mesh, or this case. So if you export the mesh, the mesh can be used in different fluent cases, but for the moment we will just save the project, and then if we click save project, the workbench project itself will be saved. And you can see here now we have this tick next to mesh, because we already have the mesh creation part of our project is already done. So what we can do is we can click switch to solution, and it will transition into ANSYS Fluent, where we can set our simulation up. Or we can close this window. Okay, we don't have to worry, we can quit the application, and we can double click on setup, where we'll go to ANSYS Fluent to set the simulation up.